This talk is based on a recent publication on a special issue that Luisa and Pasquale had edited last year, and then all references and a deep insight of what I'm going to talk today you can find here. So we started with the world of natural systems, and this is the world of material and physical systems. So we find different kind of natural systems from rocks to robots to tornadoes to planets to comets to fire flames to self-organizing reaction chemical reactions, swarm of fishes, satellites, galaxies, trees, bacteria, tables. So this is the world of natural systems. And then we have another world, which is the world of inferential entailments, which is the world of mathematics and the formal systems. So science in somehow consists in bridging into relation these two entailment structures. A material one, which is the natural system that is governed by causality, and a mathematical one that it is governed by inferential rules. So when we bring together and into entailment when we bring into relation these two entailment structures, we can say that we have a theory. And we can explain by using formal systems the natural systems. So in a bit more detailed way. So we have a natural system that it is governed by its own causality. And then we can measure, observe, and encode this causality of the natural system into a formal system which has its own rules of inferential entailments. If this formal system can explain the features of the natural system, we can say then that we can make a decoding, which is a prediction or a postdiction of the system. If this postdiction or prediction of the features of the natural systems are already encoded in the formal system, we can say that we have a model and the formal system acts as a surrogacy of the natural system. So we can study already the formal system without going to the natural system, and we can study the properties of the natural system and see how behaves the natural system in order to decode into the natural system. And when this happens, when this relation is established, we can say that we have a natural law. From this modeling relation have different, of course, shapes. So we can have a natural system that has different models. So we can see here in B, for instance, the formal system 1 is it's a model of the natural system, but we can have another model. So we can have, and this can go on. The other way it's also possible. So we can have two different kind of natural systems having one model. So in this case, for instance, the movement of the dynamical laws, the formal systems of Newton, the dynamical laws of Newton, can be the surrogate for many things that move around the universe. So we can see planets, we can see comets, and we can explain with the formal system. We have the case also in D that we can encode from a formal system another formal system too, to attempt to surrogate not only the first formal system, but also the causality of the natural system. So basically, science works like that. So from all natural systems, we have the non-living things. And also we have the living natural systems. Although there can be some controversies, for instance, whether the Earth is alive or not. But at least we can approach this phenomenologically. I mean, we recognize what it is alive because we are alive. So a thought experiment could be how we can code and program, for instance, in the search of extraterrestrial life, a machine that can tell us whether if it finds something in another planet could be alive. So at the moment, there is no possibility of that, but we know that at least phenomenologically, we distinguish what is life and not life. So what kind of natural systems are living systems? I think so that we must start all the time when we want to distinguish from this little book of Schrödinger. Schrödinger, in this book, proposed two features, very important features, which is the negative entropy that explain about the relation of the system with the environment, and the code script, which is he attempts to say that it is kind of an order or organization in the system. So according to him, these features determine the causal regime of the system, of the living system in this case. So negative entropy basically is that the system is feeding on negative entropy, because by the second law of thermodynamics, all natural systems tend to dissipate. So we have here the ink in the water, and it dissipates through time. So Schrödinger considered that these features, the negative entropy and code script, are not the opposite, but make the system to not dissipate. And then he said, as he did not make a formal theory of that, he said we must be prepared to find a new type of physical law, which when he says about physical law, he's talking about a causal regime. Because do not forget that all natural systems are governed by causality. And it came, I'm going to make short the story, came because there are many proposals, but I am focusing on the idea that the causal regime of autopoiesis do not allow the systems to dissipate. So we have a network, to make it short, a network of reaction network, a metabolic reaction network that produces molecular components which determine the system to be bonded, that and allows and specify the metabolic network doing the same thing. Of course, the system is open to energy and matter. So this is a causal regime, a circular causal regime, where systems self-determine its own molecular existence and reactions through this organization, through this circular organization. So there must be a causal organization of self-construction by operational closure, because it closes upon itself in a dynamic and thermodynamic openness. At least this is the basic features what Autopoiesis proposes. So to make it easy, they just make a circle like that to figure out how the circular organization must be in a dynamic and thermodynamic openness. So the exchange, it is coupled with its environment. So when we see again, so the attraction of the autopoiesis is again a metabolic network that produces and fabricates a boundary, and the boundary specifies and allows the metabolic network keep producing the boundary. So there is operational closure. Of course, when we put together this idea, this abstraction with an abstraction of the environment, we have the process of the living. So Maturana said that this is the necessary and sufficient condition for the constitution of living systems, and that they existed only as long as the autopoietic organization is conserved. So basically, he's saying that I break stop. The autopoiesis disorganization remains invariant. So as long as these organizations keep going on, living systems don't die. But of course, this is under structural dynamical changes. So you can see here that as long as the organization remains invariant, the living system can change its structural network inside it. So autopoiesis, it is not a definition, not a postulate, or not an a priori proposition, not a philosophical proposition of a formalization of the phenomenon of life. It is what happened in the actual realization of the living of a living system. Autopoiesis is a living system, is its living in the continued realization of their self-production or self-fabrication without the participation of any organizing principle. Maturana said, I insist the reader read my work as a biological explanation of a biological happening. So what he's saying, that autopoiesis is not a model, is not a theory, a principle, a definition of life, a property. It is the causal organization of living systems as natural systems, such that when it stops, they die. So we can consider, therefore, that every autopoietic unity is a natural system in the modeling relation of Robert-Rossi. So we cannot say that autopoiesis is a formal system. Autopoiesis is actually what is happening in all of us. And if autopoiesis stops, if this self-producing, self-constructing, and self-fabricating organization stops in us, we die. So we as natural systems, we are autopoietic systems. But it is a natural system. So we are in this world, in the world governed by causality. And we have, when we distinguish a living system as a natural system, an autopoietic system, there is a distinction of two domains of existence. So the self-producing organization, when we see the organization in itself, and the relation within the environment, so which is the structural coupling or cognition. So we as observers, we can distinguish this, the phenomenology of living systems as autopoietic systems. And therefore, as autopoiesis is a natural system, is better cast as a natural system, we can make, of course, a theory of how we can formalize this self-producing organization. So as all natural systems, we are amenable to be formalized as well. And therefore, there are many models that have been proposed for the self-organization and also for the structural coupling or cognition. So I will go explain a bit. I mean, we can at least classify the all formal systems and models that have been proposed for autopoiesis, for the self-producing organization, which can be more or less be Turing machine. This means that they are computable formal systems of autopoiesis, and they are the non-computable formal systems of autopoiesis. So the question is, we have here a theory of autopoiesis. So we can say here, the collection of these models, the cartography of these formal systems represent the theory of autopoiesis, considering that autopoiesis is a natural process. The same happens if we make a cartography of formal systems of cognition. So different formal systems have been proposed to cast what happens when autopoietic system is in its environment. And we can make also a classification of them. We can say that some of them are Turing machine computable, and others are not. We can also say a subclassification that some of them are reactive and some of them are anticipative. So when I say Turing machine, I want to say here that they are they can be implemented in rules that are pre-stated. So we pre-stated the rules and we make the rules, we code the rules and we run the rules in the computer. While there are the other models that they do not allow, they do not allow a kind of, they are not amenable to be Turing computable. When I say reactive, I am basically talking about systems that works with feedbacks. So this is very important because a feedback is a processes that happen before a behavior of a system. So if the system is deviating from a trajectory, it happens that the system self-corrects, so come back after it deviates. When I talk about anticipative models, I am saying that the system is able to predict that in the future is going to be, in a potential future, without violating causality, it's going to be some change, and not plan, the system plan, based on that prediction, how it's going to move, and therefore it's prepared, it's ready for this potential change or potential deviation, we will say. And there are another formal system, which is another formal system that Varela pushed forward, which is the calculus of reference, that it is neither Turing machine, but neither anticipative nor reactive. So it's a kind of a very, it really belongs to the formal system world. That the relation, the modeling relation with the actual, with what's happening in autopoiesis is a bit difficult to make. So for this presentation, I think that as an example to study the models that have been proposed, I selected at least the four ones. So I select a one that it is Turing computable, but it is anticipative, which is the active inference of the free energy principle that was developed, inspired in autopoiesis, in the relation of autopoiesis with its environment. There is the self-referential non-trivial machine of Heinz von Foster. There is the MR system that Robert Rosing himself did not propose as a model of autopoiesis, but later authors think that there is a modeling relation between these two, the autopoiesis and the formal system, the MR system, and then we have the calculus of self-reference of Varela. So I will focus in two. I will focus in the active inference, which is computable, tractable, and is anticipative, and in the MR system of Robert Rosing. So you can see how the modeling relation happened with active inference. So active inference is telling you that the system, autopoiesis, has internal states, and has a boundary that it is made of active states and sensory states. And there it's coupled with its environment as an external state. So we can see here the external states are the environment of the system, the internal states it's what's going on inside the system, and the active and sensory states are the relation with the environment. So based on the active inference, we can say that the system is updating as is a model, an anticipative model, a predictive model of the living being of autopoiesis. The system can predict, can make prediction errors because in the whole space of physiological states as sensory states, the system found some boundary of homeostatic states which are more predictable. So it can minimize surprise in order to keep its organization, its living in order to don't die. At least the model proposed that. And so based on that model, we can have that the system, the autopoietic system in its environment drive by making sense making of its environment, building up anticipatory models and act on the environment to remain, to conserve its organization, because organization must be conserved, a structure change. So you can see how this drift can happen in a living system. So we can have an autopoietic system coupled with its environment and in a drive, so in a drift, so it reproduces, and you can see that there is a structural changes if you follow the arrow, and then you can have a plethora of realizations of autopoiesis, which is the phylogeny. And then you can say that the diversity of living systems is because the different structural realizations of autopoiesis. So autopoiesis needs to be conserved while structural changes can happen, and then you have the diversity of the biosphere in this manner. The other model that it is quite interesting, and I am close to finish my presentation, is the MR system. So the MR system basically is telling you that you have a transformations, you have an efficient cause called if, which is in dotted arrow, that act on a metabolite outside the system and transform its metabolite. So Rosen itself asked, but who produced this efficient cause? And he said, there is another efficient cause in the system that take the output of B and produce F. But then we say, but who produced phi? This another, and then you can go to an infinite regress. But he found mathematically that there is an inverse map of B that can act as an efficient cause to produce using F as a material cost in this case to produce phi. So he said a natural system, a material system is alive as long as it is close to efficient causation. And it is very important in the modeling relation of the MR system with autopoiesis that the close to efficient causation is perhaps similar to operational closure, because operational closure, although it is not in a formal way defined in autopoiesis, who does the operations in the cell are the enzymes. So Rosen was well aware that when he was talking about efficient causation in a model of cell production, he was talking about folded enzymes, and not only folded enzymes. He was talking about catalytic sites that is not possible to predict a catalytic site from a DNA sequence. We cannot predict even for a polymer, and we cannot predict even the folding of a protein, a big protein, and use different approaches which are a kind of more comparison with what we have experimentally when we come to AlphaFold, which is this program, this whole research program to predict the folded proteins. But per se, from scratch, we are not able to predict. So in this sense, this kind of causal regime, which is the operational closure or closure to efficient causation, could be this new type of physical law that Schrödinger was talking. What we need indeed to have a folded enzyme, and this is a huge problem in structural biology and also in the origin of life when we talk about catalyst efficient causes, therefore, is how we can get first a folded enzyme from scratch. We need all the time so far a cell to produce a folded enzyme, and only in the cell these folded enzymes acts as an efficient cause. We cannot isolate, when we attempt to isolate experimentally an enzyme, it defaults, and it is not possible also to isolate, it's unisolable, the catalytic site. So this is telling you a very powerful message. From the model itself of autopoiesis, if we consider the MR system is the model of the autopoiesis and could be the right model of the cell of the organization of autopoiesis, this is telling you that we have still huge work to do on the origin of life and also on artificial life. So with this thing, I'm thank you so much. I'm just profiting this space to invite you to submit an edition that I am doing for Mathematical Biology Journal, which is called Non-Mathematical Models of Biological Organization. And with this, I am open for questions, and thank you so much for your attention.